Welcome back to another video, and I know I was on a hiatus for like a couple weeks due to school and all, but since my last upload, then I'm back again. Hopefully I can upload back on a consistent rate. Who knows, we'll see. It depends on school this semester really, so it's been getting pretty hectic. But regardless of that, here we have, let's actually evaluate this for fun. So we have this double integral from infinity to b and infinity to a of dx dy divided by x times y times x plus y. So I know what you're thinking. What's the first step to do? And let's actually get started. Obviously you can see from our bounds of integration, we have the bigger number infinity as our lower bound for even both those integrals. So for this to work, we can actually just reverse the order of integration. That would mean we have to multiply by -1 for both of them. But because we're reversing order of integration of our bounds for both integrals, so that means the sign still preserves. So negative times negative is positive. So we still get the same. Nothing has changed. So this means this is from b to infinity multiplied by a to infinity of dx dy divided by xy times x plus y. Okay. Now, next thing I want to do is I want to add and subtract an x and then multiply and divide a y. So this means, let me rewrite this integral, a infinity. So this is x plus y and then minus x, and then this is divided by x y square, x plus y, and then dx dy. Okay, but we can use our properties for double integrals. Double integrals can also be written as a product of two single integrals. So what I can do is I can actually move the so b to infinity, its integration is being integrated in respect to dy. That depends on the order. So I can actually move the dy over y to right next to the integration from b to infinity. So b infinity dy y, then multiply by a to infinity of x plus y minus x, all divided by x times y, and then x plus y dx. Okay, cool. So now what I can do now is let's actually decompose this into some partial fractions. So let's see, b infinity and then dy y multiplied by a infinity, and then x plus y, these cancels. So because they share the same denominator, and then there's addition in the numerator, so we can actually decompose this into partial fractions of the same denominator. And notice that x plus y, those cancel, the top and bottom cancel, so we have 1 divided by xy, and then subtract 1 divided by y times x plus y, then dx. Okay, and now what I can do now is I can actually just factor out the y from the denominator back into and multiply this in terms with our dy over y, and this way eventually later when we integrate this integral in particular, after taking out the y and moving it to the other integral side, integrating it will be simple. So b infinity, then dy y square, then a infinity of 1 divided by x minus 1 divided by x plus y dx. Okay, so now that we have that, now we can actually integrate this inside integral. So okay, rewrite this, b infinity dy y square, then that means I can write the brackets. So 1 over x, don't forget this is dx, so we're evaluating this integral in terms of x, so you have to treat y as a constant, but this won't be an issue here. So this is simply just the natural log of x, then minus the natural log of x plus y, and then from our bounds from a to infinity. And why not? We can actually, using our natural log rules, we can actually combine these into a singular natural log function. So b infinity dy y square multiply by, so this is minus, so for the single natural log, the input is under division, so x divided by x plus y, then from a to infinity. Okay, nice. But now what I want to do now is, let's actually, why don't we add and subtract a y. So then evaluating this will be easy again, like I said from earlier. When we're evaluating integrals, we want things to come out nice and smooth. So that's what we're doing, we're just manipulating our equations. So ln, and then we have a x plus y, then minus y divided by x plus y, then. And we can actually simplify this out again. So writing the same integral, dy divided by y squared, and then natural log of, so x plus y, they cancel, so we're just gonna end up with the natural log of 1, then minus y divided by x plus y. Okay, now we can actually evaluate our bounds. So, okay, here comes my trusty chair that I need to sit. Poor choice of wording. Now, when we evaluate our terms, so b infinity, and then so if we plug our, hold on, let me finish writing this out, y squared, then multiply by, okay, so when we plug infinity for x, remember this is this function was integrated in terms of x, so y's are still constant in this matter. So when we plug infinity, so x equals infinity, it's 1 minus y divided by infinity, but that tends to 0. So we're just left with the ln of 1, which is equal to 0. And then when we plug a, so ln of 1 minus y divided by a plus y, then let's convert y so that they both have the same denominator. So to a plus y divided by a plus y, then subtract the y, then it's minus, well, because minus from our bounds. So this is the negative natural log of a divided by a plus y. And then further simplification, we have a negative in the front, so we can actually use natural log rules again, so that's actually counted as an exponent. So to simply put, that means it's equal to the natural log of a divided by a plus y raised to the -1. And when we do that, we're just flipping the reciprocals. We're just flipping our fractions, so that means a plus y ends up in the numerator. And then, a plus y ends up in the numerator, and then a just ends up in the denominator, like so. Now that that's out of the way, now let me clean this up a little bit. So let me just write out what we have so far. So this is b infinity. So now this is the natural log of a plus y divided by a, then multiplied by dy y squared. I just put the dy outside of the, just out in the furthermost right, so it just looks smoother and nice that way. Smoother is not the word to use to describe this, but anyway. Okay, now that we have that, let's actually use natural logs again to compose this into two different natural logs, so it's under division, so we have to actually subtract natural logs. So, let's see, b infinity, so this is, this is ln of a plus y, okay, and then subtract ln of a, okay, and then multiply by dy, and then divide by y squared. So with that, let's actually distribute y squared to both of our natural log subtraction. And what we can do is we can actually use our rules of integrals, and we can actually split this into two singular integrals of the same bound. So to put it simply, so when I distribute y squared, so this is b infinity of the natural log of a plus y divided by y squared dy, and then subtract. Ln of a is a constant, so I'm actually just going to move this outside the integral. So ln of a, and then the integral from b to infinity of 1 divided by y squared dy. Okay. Now, this integral is actually pretty easy to evaluate, so just for the sake of it, let's actually just calculate this and get this out of the way before we evaluate this integral here. Mark an arrow over here. So this is just specified this integral we're calculating. So this is ln of a, and then now the integral of 1 over y squared. Now 1 over y squared, I can write this as y to the negative 2, and then when we evaluate that, so it's a plus 1, then yeah, it's so it's negative 1 over y, but there's a negative out front, so I can distribute that so it becomes positive. So that means simply it's just ln of a, then multiply by 1 divided by y, evaluate our bounds from b to infinity. So when we do that, we plug infinity. This is just 1 over infinity is just 0, and then when we plug b to here, so this means this is just equal to don't draw an arrow, just put equals since this is for here. So simply this is actually this term here in particular is ln of a divided by b, the negative because it's minus. Okay. Okay, so far we have the following: infinity ln of a plus y divided by y squared dy, and then subtract ln of a divided by b. So let me actually just box this just to reiterate what we have so far. Oh, and my green marker's out. Nice. Very nice. Well, I guess we're gonna draw this in black. Okay. Not our final answer. I just want to reiterate what we have so far. So far, it's the infinity from, or integral from b to infinity of ln of a plus y divided by y squared dy minus ln of a divided by b. Okay. So now, next step is going to be interesting. So now that we evaluate this piece of the integral, now we have to evaluate this piece. So obviously, what we're going to do now, we're actually going to do a u sub, but I shouldn't say but, because I'm just going to like define our different variable. So what I'm going to do now is when we're evaluating this integral, I'm going to let z equals 1 over y. Then this means dz is equal to negative 1 over y squared dz, or dy, like that. So this is, I'll just put negative dy, then divided by y squared. Okay, so that means this will cancel. And don't forget, we're doing a change of variable, so that means we have to change our balance of integration. So when infinity is equal to y, that means our new bound is going to be 0. And then when we plug b, so our new bound is going to be 1 divided by b. And we have ln of a, ln of a plus 1 over z. Okay, and then dz, and then minus from ln of a divided by b. Okay, so now let's actually, forgot to put the negative here since from our negative dy y squared. So, but notice 1 over b is bigger than 0. We flip our signs. So this means this is 1 over b, 0, ln of a plus 1 over z dz, and then minus ln of a divided by b. Now, we're gonna actually, now the only way we can actually integrate this piece here is just use integration by parts. So let u equals ln of a plus 1 over z. Then du is equal to, let's see, 1 over a plus z, and then the derivative of the inside is -1 divided by z squared. Okay, and then that's being divided by a plus 1 over z, then dz. Then dv equals dz, then v equals z. Okay, now let's actually plug our pieces together for our integration by parts formula. So that way we have, I'm going to write this in brackets so we can actually evaluate each term separately from our bounds. So z times a divided plus z, that's from 1 over b to 0, then minus 0 over b times du. Okay, so when I multiply z into here, so we get negative z divided by z squared, so that's -1. Okay, and well, since this is a negative out here, so I can just factor it out, and then so this will be positive. Yeah, this will be positive. And so z here, so this means this is 1 over z, and then divided by a plus z, so it's the same thing as 1 over z multiplied by 1 divided by a plus z squared. So I can just multiply I can just multiply it out, so this will just be 1, and then divided by let's see, 1 over z, and then okay, then the z, so this is just going to be, and I'm just gonna flip our terms, so it's commutative, because it's commutative, so this will just be 1 and then plus ac dz. And let's actually first evaluate this bound at z equals 0, so that means 1 over b, so that means this is 1 over b ln of a plus, let's see, 1 divided by 1 of b, so this is just b. Then when we plug 0, then obviously 0 times any number is just going to be 0, so that cancels, so we're just left with this term. Then plus this is so u sub, so we let u equals 1 over a z, so that means okay, so it will be 1 over a and then ln of 1 plus az, and then that's being evaluated from 1 over b to 0, and then we have our minus ln of a divided by b. Okay, I'm gonna need to sit for this. Okay, when we plug 1 over b, so we're plugging 1 over b for z, so this is just listen, I'm just gonna write this out again. So 1 over b ln of a plus b, then plus 1 over a. So this is just ln of 1 plus a divided by b. Okay. And then multiplied by 0, or minus our, when we evaluated this at 0, so this is 0, so ln of 1, so that's 0, so that cancels. Okay. And then, alright, so then now we're left with ln of a divided by b. Okay. And now let's actually get a common denominator for here. So this is actually just a plus b divided by b. So I'll write this out again. A plus b plus 1 over a, then ln of, let's see, let me just make sure I'm right. B. So yeah, a plus b, then divided by b, then minus ln of, should have wrote the parentheses, but whatever, it's okay. So it's the same. And now that we have that, now I can use our natural log rules and decompose this into 2 natural logs. So 1 over b, ln of a plus b, then plus 1 over a. Then I'm gonna write the bracket, ln of a plus b, then minus ln of b, and then minus ln of a divided by b. Okay, so notice that ln of a plus b, they share the same base, but then we have 1 over b and then plus 1 over a. So we can treat that as an exponent for 1 over b and plus 1 over a as using our natural log rules. So this is ln of a plus b divided by 1 over b plus 1 over a, and then minus, minus, and then we have 1 over a multiplied here, then minus, so it's a positive. Using natural log rules, they're actually a product of the inside, so this is the natural log of b divided by 1 over a, and then multiplied by a raised to the 1 over b. And then finally, using natural logs, we get that this is equal to the natural log of a plus b raised to the 1 over b plus 1 over a, then divided by a 1 over b, and then b 1 over a. Wow. Okay. So, in conclusion, our double integral from above is equal to ln of a plus b raised to the 1 over b plus 1 over a, then divided by a raised to 1 over b, and then multiplied by b raised to the 1 over a. I'm already sweating, that's crazy. It's a cool integral.